So what I would like to talk about this time is logistic regression. Now, obviously, you've heard about this before. If you haven't, you probably should take this class next year. But I assume you've heard about it in FE 201 and 202. You've heard about it in biostatistics. So again, I want to review some things just to refresh your memory, and then maybe give you some heuristic ideas about things that are important in understanding logistic regression, why we do it, what our options are, and what some of the issues are. And I want to motivate the logit transform. Okay? So the first question is, okay, it's 0-1 data. I told you that linear regression was robust, so it's not normally distributed. Regress it against the predictors. Big deal. And in fact, in econometrics, they do this a lot. And the reason they do it is they would like the outcome to be on what they think is the natural scale, which is the probability of something happening. And so if I regress the expected value of a 0-1 outcome, the expected value of a 0-1 outcome is the probability that it's a 1, right? So I regress the probability that it's a 1 against various predictors. My results are this exposure, if it goes up by 1, it changes the probability of having that outcome by beta 1%, right? I get a prediction on the probability scale. Now, that's pretty nice. So what are the problems with that? Well, one of the problems is the economists don't do case control studies, right? So if I do a case control study and I match every case with a control, what's the average probability that you're a 1? It's 50%. That's not so interesting. I mean, I can still look at what the effect of age is on being a 1 on the probability scale, and I may, but the baseline rate is some arbitrary number that depends just on, your matching ratio. So it's less interesting. So they don't tend to do that, so they don't have to worry about that issue. But there's another issue, which is if I do that, and I have B1, X1, and B2, X2 predicting the probability that you're a 1, there's nothing there that says that that predicted probability has to stay between 0 and 1. Now, I'm old enough to remember when George McGovern said that he was behind his vice presidential nominee 1,000%. And I also remember that the guy quit 2 days later, right? So predicting 1,000% is maybe not something we want to do. And we also don't like negative numbers because we don't want to bring people back from the dead. It's not a pretty thing. So we don't want that. Or that. So that's perfectly possible in what we saw on the other side, because B1, X1, B2, X2, some of those variables probably are protective, so they reduce your risk of dying, let's say, or being a case. And so for very high values of blueberry intake, we can be predicting negative probabilities of dying. Blueberries aren't that good, right? So the problem is that our left-hand side has a limited range of variation, and our right-hand side of that equal sign doesn't. So we need to fix that. So that's what the logit transform does. The log of the expected value of y divided by 1 minus the expected value of y is a plus bx, right? So what happens as the expected value of y approaches 0? Well, for values of x where the expected value of y is approaching 0, I get something that's approaching 0 over 1 minus 0, which is approaching the log of 0, and the log of 0 is negative. It's negative infinity, right? So as I approach 0, I can get very large negative numbers on the left-hand side of the equal sign. On the other hand, what happens if the expected value of y approaches 1? I have some x's that are making it very likely that you're a case. Okay, so the expected value of y is getting close to 1. Well, 1 minus the expected value of y is getting smaller and smaller. And 1 over small is big. So this thing is blowing up. It's getting to be the log of a big number. It's getting big. And so this transform can approach very large negative numbers or very large positive numbers. And so it has a similar range of variation possibilities to the variables on the right-hand side of the equal sign. So everything is cool. And that is one reason why we do a logit transform, okay? Just because it gets rid of this mismatch. Notice, however, that when we do this, that the expected value of y does not vary linearly with x, right? And that is going to create some issues for us. So yeah, this is a way to fix that up. We're going to pay a price for it. So I'm modeling not the expected value of y as my dependent variable on the left-hand side. I'm modeling a transformation of it, right? The log of the odds. Now, that means that if I compare a logistic regression to a linear regression, the right-hand side is the same. The difference is what we did on the left-hand side. We apply on the linear regression, I say the expected value of y depends on my x's. On average, blood pressure is B0 plus B1 times your age plus B2 times your body mass index, etc. On average is expected value. In the case of the logistic regression, the right-hand side looks the same, but the left-hand side is the log of the odds. It's a transformation of the expected value. So it's saying that the ratio of the odds depends on B0 plus B1 age plus B2 body mass index. So I'm estimating how a transform of the expected value of being hypertensive depends on those predictors. And that's an important thing to realize. And we're going to talk about other regression models later in the course, but they're all going to have that same feature, that the right-hand side is always the same and the left-hand side is some function of the expected value of the outcome. Okay? In this case, it was the logit. So on the transform scale, if I regress against age, I'm fitting a straight line here, right? So this is the logit of the probability that y equals 1. And if I regress it against age, I'm saying that increases linearly with age with some slope that's beta 1 hat. The coefficient is the slope of the line. That, remember, if I transform back to the probability scale, says that the probability of being a case starts very low for young people, increases, and eventually everybody is a case if they get old enough. That's what I'm assuming when I do this transform. Okay. And let's come back to this expected value point, right? The actual raw data is 0 or 1. But I can't take the log. I mean, I could take the log of 0, but I would be unhappy, right? So what we, in fact, take the transform of is the expected value of the probability that y equals 1. And we take the log of the ratio of the expected value to 1 minus the expected value. And in general, that's what we focus on in regression. We focus on predicting the expected value, although we will mention one alternative later in the course. Now let me give you another motivation. So that's one reason why we do logistic regression. Let me give you another motivation, and the other motivation comes from that S-shaped curve. That, remember, if I regress the logit of the expected value of y against age, I get a straight line on the logit scale, which is some S-shaped curve with my predictor on the real probability scale. So why do I get a curve like that? Why would I think that's reasonable? So imagine I work for, Amalgamated Toxic Dumping, your friendly local chemical company, and I make agricultural chemicals that farmers spray on their crops to kill pests, right? And so one of the things I need to tell the farmers is what the right application rate is. How many pounds per acre do I spray on this crop in order to kill the bugs? So I need to know how much it takes to kill bugs, right? So the problem is that bugs are sort of like people. They're not all the same. So that you got those wimpy little bugs, and they just curl up and die, right? And then you got those mean, tough bugs, and it takes more to kill them. So there's presumably a distribution of what in the field is called tolerance. Now to me, tolerance means I'm okay, you're okay. But in this case, tolerance means I'm okay, you're dead. Because tolerance is the dose up to which you tolerate the drug, the pesticide, and above which you die. Okay? So there's a distribution of fatal doses in the population of bugs. Okay? So let's say this is the distribution, right? Then we have some dose over here. And if I give that dose to my crops, spray all the bugs, then obviously the bugs for whom that is the highest tolerable dose and then they die are going to die. But the bugs for whom this was the highest tolerable dose, if this is the dose I apply, they're going to die too, right? So the number of dead bugs I'm going to get is in fact the area under this curve. Because at that dose, all of these guys will die. On the other hand, all of those guys are going to stay alive. So if I'm Farmer Brown, I'm not very happy about that dose, right? Okay. So the probability that a bug is dead is therefore the probability that the tolerance level for bug I is less than whatever my exposure is, whatever my dose is. And that is clearly not linear in the dose, because it's some cumulative probability distribution, right? It's the area under the curve up to dose I. And so if, as I go to higher and higher doses, this area is increasing non-linearly. And when I get past here, it's increasing by less and less, so it's quite non-linear. So it looks something indeed like this. This is a cumulative probability curve, which is exactly what that logit transform was doing. So in fact, that's one other reason why we do a logistic regression, because their logit is the cumulative probability distribution of some probability, which is in fact the Bose-Einstein distribution, for those of you who remember your college physics. But in any case, it's a cumulative probability distribution, and the underlying distribution looks bell-shaped like a normal distribution does, but it's not in fact Gaussian. The tails are a little fatter, a little higher than you would get for a Gaussian distribution. Okay, so clearly we could use that and get one of those S-shaped curves. We could do a cumulative normal distribution, and that's called a probit regression. Historically, the reason that we haven't done that is that you can calculate analytically what the logistic distribution looks like, what this cumulative probability distribution looks like. You can write down an algebraic expression. That makes it very easy for computers. Back when computers had cathode tubes in them, right? That was a big deal. Whereas the cumulative Gaussian distribution doesn't have an analytical form. You have to actually numerically integrate it. Well, your phone has more computing power than my university had when I was an undergraduate. So this is not such a big deal anymore, right? But historically, that's why a lot of people didn't do probit models. And it is the cumulative normal. So if you think the distribution's normal, that's nice. And then there's the complementary log-log distribution, which has even fatter tails than the logistic. One argument for using the logistic, or the Gompertz is the other name, rather than the cumulative normal, is the observation that most variables that people tend to think of as surely normally distributed in practice actually have fat tails, like the distribution of height among 25-year-olds or other things like that you would think are normal. Nothing normal. Gauss developed the normal distribution by looking at the errors in measuring the locations of stars. He was, among other things, an astronomer. It is the distribution of error. But the reason why people have different heights is not error in measuring their heights. It's we don't know all their genes and what they ate when they were a kid and stuff like that, right? And that tends to give you fatter tails. So it's not such a bad idea that we wound up with the logit. And the logit has this other nice feature that if I calculate the log of the odds at some exposure and the log of the odds at an exposure 1 unit higher in whatever my exposure variable is, and I take the difference between this and this, right? The difference is just B1. And so if I exponentiate that, and that's the log of the odds. So if I want to get the odds ratio, I exponentiate the log of the odds ratio, and that's e to the B1, and that is the odds ratio. So it gives me a nice way to calculate the odds ratio. Now, probit regression gives you a rate ratio, which is a nice thing to have, actually, but not for a case control study. Because again, you know, the probability of being a case mostly depends on how many controls you sampled, right? Whereas the odds does not depend on how many controls you sampled. And so I can easily compare this across studies, okay? That brings us to where this binary data came from. So just remember, one important source of binary data is case control studies. But we also have binary data from cohort studies, right? I can go out and I can recruit a cohort of people, and I can ask them whether or not they have asthma. I can check their medical records and confirm that, right? So now I have yes, no, they have asthma. Or I can follow them for 10 years and look at the incidence of asthma in the population, right? And so they're 1 if they had a case, 0 if they didn't become asthmatic. And again, I have binary data. So whether I'm looking cross-sectionally in a cohort or longitudinally in the cohort, I might have some 0, 1 data that I want to analyze in a logistic regression. And in the case of case control studies, different matching strategies are going to lead us to do different kinds of analyses. So that in particular, if I have matched sets of people because I've stratified, you know, I've sampled my people not randomly, but I've matched everyone by age. So I have matching variables that I use to pick my controls. Then I need to take that into account in my analysis, and that could be done in a logistic regression with indicator variables for all of the matching variables and their interactions, but that may not be feasible, in which case I'm going to do a conditional logistic regression, which we will talk about later in the course. So that's a review of logistic regression. What are going to be the problems? Well, the first problem is that looking at the data is a lot harder, right? I mean, I can look at blood pressure versus age or number of deaths per day, as I showed you, versus black smoke level and try to get an idea of what's going on. But if people are all either a 0 or a 1, right, and I try to look at a plot of that, it's not going to look very informative. Again, though, if I divided people, if I sorted people by increasing order of exposure and divided them into groups of 20 and took the mean, then in general I will get a number that's between 0 and 1. Take the average of the ones and the zeros in this group and plot it against that exposure level. And in the next group, I take the average and I plot it, etc., etc. So that kind of approach is going to become key if you want to take a graphical look at the data, because having a line of 1 and a line of 0 and dots, that's not going to help you very much. Second issue is the interpretation of the coefficient. The coefficient is the increase in the odds, in the log of the odds of having an event, of being a case, for a 1 unit increase in exposure. And that's a little bit more complicated than, oh yeah, it's the slope, delta y over delta x. It is the slope on the log odds scale. But it's the log odds scale, not the odds. Okay. If I'm not doing a match case control study, maybe I would like to know what the probabilities are. How does my exposure increase the probability of getting this condition? How can we do that? And, you know, we need to think about the issues of covariate control for logistic regression, just as we did for linear regression. And basically, it's the same idea, but there are some special features of logistic regression. So the nice thing about controlling for a variable in a linear regression, right, is the following. Suppose I have a variable z, which is related to my outcome, but it's not correlated with my exposure. It's not a confounder, right? Whether I put z in or not will not change the coefficient that I get for my exposure of interest. How do I know that? I'll show you in a minute. But first, in the case of linear regression, I might still want to leave it in the model because it explains some of the variability in the data, which reduces the noise in the data, which actually tends to give me smaller confidence intervals for my slope relating exposure to outcome, because it's easier to see things when there's less noise in the data. So I might want to include z even if it's not a confounder, just because it explains some more variation in y and shrinks the standard errors of x. Okay? Now, that's not true in logistic regression. Let's look at linear regression first. Okay? So up here is the truth. Here's the truth. The truth is that y depends on x and it depends on z. However, it's also true that z is not related to x. So z is not a confounder because the distribution of z is the same in people with low x and with high x. And so it is randomized with respect to x. I don't need a control for it. What happens if I don't? Well, the expected value of y given just x and not z is, let me take this whole thing here and take the expected value of that just given x, right? So I get a is a, it's a constant. The expected value of b1x given x is b1x. The expected value of b2z given x, well, x isn't related to z. So that's just equal to b2 times the expected value of z. Because on average, what is b2z given x? X is unrelated to z. That's just on average, what is b2z, right? Which is some number, right? So I get a number, b2z, which is a constant because it's the average of b2z, which is just b2 times the average z. I add that to a to get a star, and b1 is the same. It hasn't changed, right? So in linear regression, I leave out predictors of y that aren't related to x. It's fine. I get the same b1. Don't have to worry about them. The reason that works is that the expected value of y is linear in the predictors, right? It's an effect due to x plus the effect due to z, right? It's additive. So let's say z is a binary variable for convenience. So if z equals 1, then b2 is 5. So if z equals 1, on average, my, let's say, blood pressure is 5 millimeters higher. That's true whether x equals 0 or x equals 2. I mean x equals 1, right? And so if I subtract the mean value of y when x equals 1 minus the mean value when x equals 0, right? I added 5 to both of them because z was equal to 1. Those 5 subtract out, right? And the change in y for a 1 unit change in x going from 0 to 1 doesn't care about what z was because the z's subtracted out. And that's the same thing when z equals 0, obviously, it's just not there, and I get the same b1. I get the same slope for x. The logit, this is not linear or additive in x and z, and so the same thing doesn't happen. So let me show you that. But first, let me show you that for most other things, we're better off than for logistic regression. So let's take a rate ratio model, either a Poisson regression or even a Cox proportionate hazard model. Suppose the expected value of y given x and z is really this. Well, I can factor that, right? E to the a plus b is e to the a times e to the b. So I can split that up into the part depending on x, b0 plus b1x, I throw the intercept in here, times the part that depends on z. So if I leave out z and calculate the expected value of this, given x, it's just the expected value of this part given x, which is just that, right, times the expected value of b2z given x. But x is unrelated to z. That's what we're talking about. That's the scenario we're describing. X is unrelated to z, so this is just the expected value of b2z, right, which is some constant, which multiplies this. It's like, you know, so that's going to change b0 again, but it's not going to change b1. So if I have a relative risk or rate ratio model, everything is also cool. It's not additive, but it's factorable. Unfortunately, the expected value of y given x and z in a logistic model is e to the b0 plus b1x plus b2z, just like here, divided by 1 plus e to that. And this does not factor into a part that depends on x and a part that depends on z. So we're screwed. Let me illustrate this now more simply with 2 by 2 tables, okay? So here's a 2 by 2 table, right? And what I have is, this is for one level of z, okay? So this is for z equals 0, and this is for z equals 1, right? So for z equals 0, I have 20 people who aren't exposed to my exposure of interest and 20 people who are, right? And this is how they distribute between whether or not they had an event or not. And I can calculate the odds ratio here, which is 10 times 15, which is 150. 5 times 10 is 50, so I get an odds ratio of 3, right? Now over here, what about the people with this z equals 1 group? Well, the numbers are different here, but it turns out that 5 times 18 divided by 2 times 15 gives me an odds ratio of 3 also. So whether z equals 0 or z equals 1, I get an odds ratio of 3. And z is unrelated to x. Why? Because when z equals 0, the expected value of x, there are 20 zeros and 20 ones. When z is equal to 0, I have 20 values for x equals 0, 20 values for x equals 1. And similarly, when z equals 1, half the people have x equals 0, half the people have x equals 1. So there's clearly no association between the level of z and the value of x, okay? And in each strata of z, I get an odds ratio of 3. Now, let's put all the data together. I combine the data, and I'm going to leave z out. I'm not going to stratify by z, just like in the linear regression and the rate ratio regression, right? So I add up for, x equals 0 and y equals 0. I got 5 and 10. That gives me 15, etc. for all these others. And now I don't control for z, and what happens? I get an odds ratio of 2.8, not 3. This is kind of disturbing, right? Because what you get for your odds ratio depends on which covariates you control for, even when the covariates are not associated with your exposure. This is why logistic regression is a little funky. So we can't really use the 10% solution for choosing variables in the case of logistic regression, because I can put in a variable that is not a confounder and change the odds ratio by 10%. So lasso is looking a lot more attractive in this scenario, but I still need to decide which odds ratio I want, because they're not the same. So this is one of the difficult aspects about logistic regression. And in logistic regression, we do not have robust results. Logistic regression is sensitive to many things. It is not robust, doesn't behave as well as other forms of regression. And that, unfortunately, is life. So, thank you, and we'll try to do some work with logistic regression on the computer so that you can get a feel for all of these things.